Hi, my name is Jeff Coronado from JCSE, and this is a session in Bridging the Gap. Okay, the session that we're going to be jumping into here is W17-1. And in particular, we're going to be focusing on the roof outrigger and the roof outrigger connection in that detail. So a couple of things that we're going to be covering in this particular session is the uplift resistance of an outrigger and the correct load duration factor to use when we're dealing with timber design. Um, and we've got a roof framing element. Okay, so with that in mind, let's take a look at what our detail looks like. And schematically, this is a detail for an outrigger. Okay, so this is one way of doing it. There are several ways that we can go about doing an outrigger. And if you're still not quite clear on what we are referring to as an outrigger, let's just say, hypothetically, if we look at the top of a roof, and probably this is going to be most applicable in residential construction. So let's visualize a roof um, from a bird's eye view point of view. And let's say here's our ridge. Okay. And let's say the interior walls kind of lay out something like this. And I'll draw another line there, another square. Okay, so this is the orange here is the wall that you really can't see, right? You really can't see this from a bird's eye view perspective, but we know that they're below the roof. So this is the walls that support the roof around the perimeter, um, in this case of a residence. So the outrigger in particular that we are looking at is kind of what's going on right here. If we were to slice a section right here and look this way, this is what we would be looking at, right? So we have the roof joists or roof rafters, whatever the case may be, right here. Um, Probably rafters. There might be a ceiling below this. Here's our roof rafters. Here is the exterior wall. All right. And so we know that the roof doesn't stop right at the edge of the wall, right? The roof does not stop at the edge of the wall. There is a little overhang of roof. And that's what this area is. There's a little overhang. So we somehow need to support that, right? Sure wouldn't want to be the roofer that goes out and is trying to do his job and is trying to roof this re-roof, let's say re-roof or roof the roof, and he goes out there and steps out here for whatever reason, goes out and steps out on the edge, and boom, he falls, right? Or they fall. The case may be the young lady, the young man falls because they stepped in this area and there's no support for that. So clearly, as structural engineers, we want to provide support for the outrigger, for the overhang of the roof. Okay, so let's dive into how we would do that. Um, okay, for our purposes as engineers, um, we are schematically, no, I don't know about schematically, conceptually, maybe. Conceptually, we would look at that outrigger as a beam. That's how we would model it. We would model the outrigger as a beam, and we would look at it as a simply supported beam with an overhang. So here is one simple support. Here is your second simple support. And then there is an overhang out here. So it's a simply supported beam with an overhang. Um, so let's see, connection. So in particular, we want to focus on this connection here, because if we have uplift, that's where we're going to see the uplift. Now, keep in mind, keep in mind that as simple of an element as an outrigger is, it does have some interesting loading that you do need to consider. So if we try to well, no, let's not even try to do that. Let me just use let me draw a couple lines for you here. So let me do this. And in blue, so here is our outrigger. Well, there's several load patterns that we need to consider in designing different aspects of this outrigger. So the one thing that we can't get away from, I can use yellow. The one thing we cannot get away from, yellow is not real good. Try another color. In fact, let me try orange. The one thing we cannot get away from is the dead load. All right. We know that we have dead load on both spans. Okay. We gotta kind of visualize and take into account that this beam, even though it's simply supported, has two spans to it, right? There is the span to the left where to the left of the simple support. So where the support here on the right side is simple, but at the other end, it's a free end for this beam. And then there's the span that's between the two simple supports. The dead load we can't get away from, right? The dead load is the dead load. That's just the roofing material. So that's going to be present on both sides, on both spans. However, the live load is another matter. So we have one condition. You have to design this outrigger for a condition. This is roof live. Okay, you have to design for when there is live load on both spans. Can you intuitively see what element of the outrigger is going to be governed by this condition? Give you a second to think about that. So I can tell you by looking at this, what that's going to give me is the maximum flexure on the overhang, right? Because this is going to curve down like this, right? And when we fully load that overhang, that's going to give me the maximum flexure at the simple support. So if I'm looking for maximum negative moment, this is the condition that would give me that. The other thing that I would get from this is the support at the exterior wall. This is going to give me the maximum reaction at the exterior wall. So whatever the load transfer is, if I'm trying to figure out what my maximum load transfer is going to be, what my maximum loading on this wall is going to be from this outrigger, this load scenario is the one that would give me that, right? Okay, let's move on to another load combination. So let me go back to blue. Different blue, that's okay. I'm also going to run out of space here, but we'll figure it out. We'll make it work. So now what happens? Okay, I'm not going to redraw the dead load. The dead load stays the same, But now let me use the light green and only put live load on the span of the outrigger that's between the two simple supports. Okay, so we're going to say there is no live load out in the area of the overhang out here. Nobody's stepping out there. Okay, what happens when the guy or the gal, gotta find a more generic term here. When the framer or the roofer is stepping in this area, but not this area, then what's my loading over here? Um, well, what I can see intuitively, and I'll let you think about it for a second. What do you think this loading is what part of the design of the outrigger is going to be governed by this condition? And in case you're saying none, no, there'll be something that's governed by that. Give it a second. What's going to be governed by this condition is your maximum positive moment on on the simply supported span. Because now if you don't have this load pushing down here, that's gonna increase the downward deflection over here. So your maximum deflection in between the simple supports, your maximum moment in between the simple supports is going to be governed by the load condition that includes dead load on both spans and only live load on the simply supported span. Now let's look at our third condition that we develop here. And this one is going to be governed, or this one is going to apply when we only have live load on the outrigger. I'm sorry, on the extension, on the overhang on the outrigger. Okay, so now that this is the situation where the roofer, the framer, the roofer is not standing out here and only happens to be putting pressure out here. All right. So whatever they're leaning over, whatever they're doing, right? They're working right on the edge. They put pressure here, but there's now no pressure in the backspan of the outrigger. So now what gets governed here? You know what? Let me extend the black lines. I think that'll help us here a little bit. So let me extend our little guidelines. Now, hopefully you can see that what we are now most vulnerable at is not much of a straight line, but bear with me, is our outrigger kind of teetering on the exterior wall, right? So now it kind of our outrigger has kind of rotated about the exterior wall because we're putting weight out here. And if there's really nothing to resist it back here, it's just gonna rotate over. Okay, so what this tells us is we may potentially have uplift on the back end of this outrigger that we are going to have to connect so to prevent this failure mode. So this loading criteria, this loading with the live load on the overhang and no live load on the backspan, only dead load. And again, remember, the dead load is always present in all three of these cases, right? Both spans have full dead load in all three of these cases. But conceivably, if we only have live load, if we have dead load and live load on the overhang portion and only dead load on the interior portion, on the portion between the two supports, conceivably we might have uplift. We might have this rotation going on that we are going to have to account for. Okay, so let me clear the screen here. because that then gets us through this, right? And again, this is all in our manual for those of you that are in-house. So you will be able to tell, oh, okay, so how do you know if you have uplift at at the overhang? How do we know if there's uplift? Well, depends on how you're doing the outrigger, if you're using software, if you are doing it by hand, but whatever the case may be, but if we are using software, then let me scroll down, and you're more than likely going to see a negative value at the reaction, um, which is this number here in this output, right? So the negative value in the load combination that is dead plus roof live load, excuse me. And again, the roof live load is only on the overhang. But in that condition, there is a negative reaction at that back support. And that tells us there is uplift that we need to account for. Okay. All right. Now, so let's pick up this point. In accordance with the California Building Code, that's the one that we're going to use as a model in this particular session. Um, we are looking at the fastening schedule. Okay, so a couple things there. So there is a fastening schedule present in a lot of our building codes. Whether we're looking at the California Building Code as we are in this case, there is a similar fastening schedule in the International Building Code. And therefore, by extension, I got to believe most codes in most jurisdictions, wherever they adopt the IBC, but then modify it, is most likely going to have a fastening schedule. So whatever the code is that applies for your jurisdiction, you can take a look and you can actually search fastening schedule, and more than likely you will find something. And this is under timber design, right? Keep in mind this detail what did we say we were covering here? Let me see if I can back up. Again, this is for those of you that are in-house. This is for W17, okay? So this is a outrigger framed from lumber. So it is the wood section of your building code that's going to govern. So in the California Building Code, and a couple things there. We can see here in this example two things. One is the year of the code, and yes, the fact that it is the California Building Code. So make sure you're using the current edition of the building code, and that you are using the code that is in force at the location of your project. Again, this table is similar to what's in the IBC. So if you are in a region that's covered by the IBC, this is going to be very similar to what you're going to find in that code as well. Okay, let's continue. Let me clear here. Let's continue. So now, what do we have? If you do not specify a connection, okay, if you do not specify a connection for the right end of the outrigger, this is a typo right here. Huh. Okay, we got to fix this in our manual. So that should not say streamer, that should say framer. So if you do not specify the connection, then the framer is going to use this table, the fastening schedule table in the building code, of which this is an excerpt, to provide that connection. So what I am suggesting here is that they will provide 1/8 toenail on each side of the outrigger. Okay, well, how do I know that that's what they're going to provide? Well, you have to go down the conditions, the cases that are covered by that schedule. And you can see here in the excerpt how they're numbered. So in particular, right now, we're covering 23 through 29. So you just have to scroll down the table and find the condition that most closely applies to your condition. Um, and you may have to use some judgment because the condition that you've got may not be exactly what's covered or how it is covered in the code. Your wording, the way you're searching for it, the terms you're using or thinking of may be different than what the code is using. So you may have to use a little bit of judgment. If you believe that there might be two situations in the fastening schedule table that apply to you and you're not sure, your best bet is to then think of the one that is has the least strength, the least capacity, right? And base your design based on that lower capacity just to be safe, just to be conservative, okay? So if you're not sure, use the one that's going to give you the lower capacity, or just specify the connection. Just specify how you want those two elements connected and not leave it up to the table and whatever the framer may interpret, right? That's probably your best bet. But okay, short of that, I'm making the assumption here that the framer is going to use this case, 29. So the bridging or blocking to a joist. Okay, let me clear the screen and we'll go back to that image at the beginning. Go back to this. Yeah, I've got this outrigger, right? I've got this outrigger. I'm connecting it to this joist. So, okay, if I'm the framer, I think it would be reasonable of me to interpret this as a block that's being connected to a joist, and that's how I would connect this. So that would be a reasonable interpretation. So I believe that was case 29. And there are several possibilities there, but based on our office standards are that we only allow common nails. Therefore, if we only allow common nails in our projects, then what that leaves the framer with is this as his one viable option. Two 8D common nails at each end of that. I'm sorry, two 8D common toenails at each end of the outrigger. Um, You know what? Let me cover this right now. And I'm not going to get too much into toenails because toenails are covered in another Bridging the Gap session. Um, but um, but just in case you're wondering, yeah, a toenail. Okay, just in case you're wondering, a toenail. Well, first of all, I don't know where that term came from, but whoever coined that term, I'd hate to see what his toes or his toenails look like. But whatever, somebody came up with the term toenail. So if you have two pieces of lumber, okay, a toenail is a nail that gets driven at an angle through the side of one member into the holding member. Okay, so this is a toenail. And so that's how this outrigger would be connected. So if we go back and if we were to look at this connection, kind of like a little plan view, little bird's eye view of this connection, let's see, what would we see? We would see the rafter, we would see the outrigger, right? And then let's just say here's the exterior wall. All right, and what we're looking at is the connection between the outrigger and this rafter here. And what we're saying is that it's going to be with a toe nail, meaning that what we're going to have is a nail that gets driven at an angle from the outrigger to the holding member, which is the rafter, and another nail likewise over here. Okay, so that's how the framer is going to connect that if they're not given any more direction from us other than what we're showing here. In essence, if we don't specify anything for that connection, then the framer is going to rely on the fastening schedule in the building code and do this. And that's a toenail. Okay. Let me clear the screen. Where are we here? Okay. Let me make this a little bit bigger. All right. Change color if I can. All right, in accordance, so now we're over here, right? In accordance with the CBC, okay, so we've got this part, right? We've covered this so far. So we're going to have 180 toenail on each side of the outrigger. Okay, let's get into the capacity of this connection. All right, so first of all, ASD, the ASD capacity of an 8D nail. Why are we talking about ASD? Well, probably if you are closer to still being in school, I think what you're going to realize is most of us in practice, when it comes to timber design, we still use ASD. I know that there's a big push towards getting us to go to LRFD. There are some inroads being made, but I think most offices are still not there yet. I think what you're going to find is that most offices still design their timber construction based on ASD practices. So the ASD capacity of an 8D common nail, right? This was given to us by the code. An 8D common nail is given in the 2015 NDS, in particular table 12N, and it shows that capacity to be 97 pounds. Okay. So the capacity of the nail in shear is 97 pounds. Now remember, we don't have this nail acting in shear. We have it acting as a toenail. It's being applied as a toenail. Not even sure I'm wording that right. But yes, it's installed as a toenail. So it doesn't get the full capacity of a nail in shear. What it gets is a factored down capacity, and it's factored down by 83%. So again, this is a value provided to you in the NDS, the 83%. Okay. So a toenail has 83% of the full capacity of the nail. All right, so now the next thing. Sorry. Now the next thing, that would be the low duration factor. So the low duration factor is covered in NDS 2.3.2, and we take 1.25. And okay, if you're biting, you can question, why do we take 1.25 for the design of a roof outrigger? All right, let me clear the screen and let's go to the table in the NDS, which is in 2.3.2. And here we have a blow up of that table. So this table 2.3.2 is in section 2.3.2 of the NDS. Here we have several low duration factors. Not familiar with a low duration factor. Maybe, maybe not. I don't know. If you are stronger in, let's say, steel design or concrete design, then sure, you may not be familiar with the low duration factor. So the low duration factor is something that is unique to timber design. What we do with the low duration factor is take into account that the wood in this sense, almost has like a memory. It knows how much over the lifetime that it exists, it knows how much it remembers. It has a memory. It remembers how long it has been loaded. The less frequently, the less frequently that the connection, that the member in timber is loaded, then the happier the timber member is, the more it can sustain that load. Hence the concept of load duration. You can see how the more frequently that the load is applied, the more frequently you can see that we go down, right? More frequently. I'm sorry, it's the other way around. Okay, I'm wording it wrong. Excuse me. So the more infrequent that the load is applied. So we start off with a load, we start off with a load that is permanently applied, right? So obviously that would be the load that is present the most amount of time. That's permanent. Then we go down 10 years, 2 months, all the way down to just an impact load, right? Something that's there instantaneously. We go down from 2 months to 7 days, 10 minutes to just an instantaneous load. As this period of time decreases, notice how the load duration factor increases, right? It's a so wood is able to resist a greater amount of load if it's only going to be present in short bursts, is the idea. Okay, so with that in mind, so the bottom line there is that for timber design, we have this factor that we have to include, which is called the load duration factor. Okay, so the less frequent that the load is present, the greater the load duration factor is. Okay, got it, right? All right, now what's the load duration factor then for this roof framing member, this outrigger? Well, let's see. We go down here and we take a look and see which is the roof condition. We see dead, live load, snow, construction, wind, impact. No roof, right? Well, Jiminy Crickets, no roof. So now what do we do? Well, not exactly. Not exactly. Let me undo this. We do have roof. Roof is covered by the construction load. Sometimes there can be a little bit of a disconnect there because we tend to call roof live load just that, roof live load, right? But if you think about it, what constitutes roof live load? I mean, if we think about it, let's even go back. What constitutes live load? What constitutes occupancy live load? Well, it's what people walking around on the floor, furnishings, right? TVs, beds, dining room tables, sofas. Um, it's you hosting maybe some friends over. All of that is your occupancy live load, right? All right. So now let's think about the roof live load, right? What constitutes roof live load? Is it people walking around there? I don't know. Seems to me like I go day after day after day, and when I look at a roof, there's nobody walking on the roof, right? It's not like your floor where there's people walking on the floor literally every day. On the roof, there's no people walking around on it. There's no furnishings. There's no furnishings, right? No beds, no TVs. So what exactly is roof live load? Well, the roof live load accounts for basically the one time every so infrequently that there is going to be construction work being done on the roof. So when does that happen? Well, it happens right off the bat, right? On day one, when the roof is being built, that's roof live load. All the laborers up there working, walking around, carrying their nail bags and so forth, that's roof live load. When they're applying the roof. And then when would there be roof live load after that? Well, probably, gosh, could be a good 20 years. It could be a good 20, 30 years might be the next time that there's a crew up there, a crew of people walking around on the roof with their nail bags, removing some old roofing, removing maybe some decayed wood structural panels, and reapplying a new roof. But it's been a good 20, 30 years, right? Over the totality of the lifetime of the structure, that roof is only going to see live load a couple times, only a couple times. Therefore, yes, the roof live load is a construction load. We're kind of estimating that at most, that roof is only going to be loaded with roof live load a total of no more than 7 days. So you can do the math. 7 times 24, right? 24 hours in a day. For those number of hours, that's about when the roof framing is going to see that live load. Okay. So the roof live load is really a construction load. Therefore, when we are doing roof framing design, we take this load factor, 1.25, is the load factor that applies for roof framing members, their connections when we're dealing in timber. Clear that. Let me see if I can move back. Okay, so now I think we pick up here on D, right? So the adjusted, now we're not talking about the tabulated value, right? Keep in mind the difference between the tabulated value and the adjusted value. The tabulated value was the one that we started with when we pick it off the table, which was the 97 pounds. Then we need to adjust it for the different factors that apply. In this case, we have a factor for the fact that the nail is being used as a toenail, and we have a factor for the fact that this is a roof member. So we use a load duration factor of 1.25. So the net result of that is that the capacity of that toenail is just over 100 pounds. Okay. Since we have two toenails, the uplift resistance of that outrigger is just over 200 pounds. So as long as our uplift is less, as long as our uplift is less than 200 pounds, we don't need to provide any more connection other than what the framer is going to provide based on the nailing schedule. If we did have more uplift than the capacity of the two toenails, then yes, we would have to specify a stronger connection. Okay. But as long as we're under 200 pounds, based on the capacity of an 8D common, right? Remember all the things that we covered, 8D common toenail roof framing, so you get the load duration factor of 1.25, toenail, so you take the reduction of 83%, that'll give us a capacity of 200 pounds. Okay, guys, real good.